Hello everyone, and welcome to some more remote learning. In this video, we're going to expand upon the concept we learned in the last video, but now we're going to be rotating around something that's not an axis, so some other line in the XY coordinate system. However, it's either going to be a horizontal line being parallel to the x-axis or a vertical line being parallel to the y-axis. So in general, we know that volume is going to be equal to the integral of some area. For disk and washer, that area is going to be built on the formula pi r squared. For disk, we don't have an inner radius, or we could say our inner radius is 0. So we're not going to have some r outer squared minus an r inner squared. However, with the washer method, we do. That's why in the previous video I said that the washer method was like an extension of the disk, or you can think of the disk method being an easier version of the washer. We don't have that hole that we're trying to remove. But regardless, the volume is equal to the integral of that area. So if I was just to think about this generally, I'm going to say that the volume is going to equal some bounds, let's just say from A to B, or you could say C to D, E to F, doesn't really matter. We have a starting point where we start drawing our rectangles and a stopping point, either in the X or in the Y. Then we're going to have pi times our outer radius squared minus our inner radius squared. And as opposed to saying dx or dy, because that could change, I'm going to just say dr from now. R sub O represents our outer radius. So when we distribute that pi through, that's pi r squared, so that's our largest area. And we're taking away that smaller area, pi r inner squared, and integrating with respect to either x or y. This is just kind of like the general way of thinking about it. And that leads us right into the important part of rotating around something besides an axis, is that our radius is no longer just going to be our function. Our radius is going to be our function and a constant, either subtracted or added together. Because remember that radius is the distance from the axis or from the line we're revolving around. So keep that in mind as we jump into this practice problem number 1. Now I kept it pretty simple for this entire worksheet. We're just going to let R be the region bounded by y equals the square root of x, which is the red function, and y equals x over 2. And there's 4 problems on this worksheet, and that region is the same on every problem. So I'll go ahead and shade in our region. In the first part, we want to find the volume of the solid generated when R is revolved about the line y equals -2. So if I was to draw the line y equals -2, I'm going to have this line here. This is what we're revolving around. Now if I'm using the washer or the disk method, in this case it's going to be the washer method because we have 2 functions that we're bounded between, so we're going to be using the washer method. But I need to think about which way I'm going to be drawing my rectangles. Remember, when I rotate those slices around, I want a disk, not a shell. So I want some sort of washer, not a cylinder. But let's think about this. If I was to draw my rectangles horizontally, and then I rotated that horizontal shape around, I'm going to get something that looks like a cylinder, which is what I don't want. So doing this way would be technically the shell method, which we'll get into next worksheet. Therefore, I know that I want my rectangles drawn vertically. And when I'm drawing my rectangles vertically, you can see then when I rotate it around, I'm going to get that flat disk or washer. Something along the lines of this, if I was to slice that. So with that being said, that means that we're going to be integrating this with respect to, well, what's that width? That width is with respect to x. It's a small change in x. So integrating with respect to x, dx. So from here, I can easily figure out my bounds to my integral. I start drawing my rectangles. Well, the leftmost point looks like 0, 0. And let's go ahead and confirm that intersection point. If I plugged a 0 in for x, the square root of 0 is indeed 0, and 0 over 2 is indeed 0. So my intersection point is 0, 0. And remember I said that I'm going to be using the same region for all 4 problems. So once we figure out the intersection points, we won't have to do that in each of the other steps. But just remember, 0, 0 is that first intersection point. The second intersection point is going to be when the square root of x equals x over 2. So solving for that, the square root of x equals x over 2 when? Well, if I squared both sides, I'd get that x is equal to x squared over 4. And then if I multiply both sides by 4, I'd get that 4x equaled x squared. And then if I divided by x, I would get that 4 was equal to x. So again, I multiplied by 4 and then divided by x to get that 4 was equal to x. So if 4 equals x, well, because I'm integrating with respect to x, I only care about that x value. But because I know I'm going to need that y value later on in this worksheet, I'll solve for that entire point. So the point is 4, comma, well, when we plug 4 in for x, 4 divided by 2 is 2, square root of 4 is 2. It is indeed equivalent. 4, 2 is that intersection point. So setting up my bounds, I care about my x bounds, so that's 0 to 4. I start drawing my rectangles at 0, and I stop drawing those rectangles at 4. So there's just a couple filled in so that you can see them. But envision them along that entire region. Now I know that I'm going to have pi times my outer radius squared minus my inner radius squared, and I'm integrating this with respect to x. I just need to figure out my radius. And remember, what is the radius? It's the distance from the axis of revolution, so the line that we're revolving around, to our function. And I care about my outer radius first, which is my greatest distance from that. So if I was to look at my axis of revolution, it's here, and my greatest distance would be all the way up to this red function. Now, originally, when we were just rotating around, let's say the x-axis, we knew that that distance was just the function itself. So we knew going from our axis to our function would give us our height, which in this case would be the square root of x. However, I have this extra length I need to take into account. This length is the square root of x, but the total length, well, what am I adding to that? What's my distance from my axis to the line I'm revolving around? That's a distance of 2. Because remember that horizontal line is -2, so that space in between takes up 2 units. So if I want that total distance, that's going to be 2 and the square root of x. So my outer radius is going to be 2 plus the square root of x. That's my outer radius, and what I'm going to do is square that entire thing. Now I need to subtract my inner radius from that. So my inner radius, same deal, except I'm going to a closer line. So I'm going from the line I'm revolving around up to the smaller radius, my inner radius, which is the closer function. Again, if I was revolving around the x-axis, I know that distance. That distance is just simply the function, which is x over 2. But my radius is the whole entire distance, so I need to add what? I'm going to need to add 2. So then this is going to be x over 2 plus 2, that quantity squared. So I have pi times my outer radius squared minus my inner radius squared, and I'm going to integrate that with respect to x. So let's go through this quickly. We're going from 0 to 4, and we have pi. I'll go ahead and pull pi out in front since it's just some constant. Distributing 2 plus the square root of x, expanding that out, that's going to be 4 plus 4 square root of x plus x. And from that, I'm subtracting, expanding this next binomial out, that's going to be x squared over 4 plus 4x over 4, which is going to be 2x plus 4. And this is all with respect to x. So to make this easier on myself, I'm going to continue to simplify down before I integrate because I see some terms that I can combine. So notice if I have a positive 4 and I'm subtracting 4, that's going to go away. So I'll have 4 square root of x all by itself, but I can combine x with 2x, but remember that 2x is subtracted, so that's going to be minus x, and then remember this x squared over 4 is also subtracted. So I combined all my like terms. Now I'll integrate. So this is going to be pi times integrating 4 square root of x. Integrating that, if I add 1 to that exponent of 1/2, that's going to be 3/2. So I'll have x to the 3/2 as my variable raised to some power, and then if I divide by that exponent, that's dividing by 3/2 or multiplying by 2/3, which is going to be 8/3 when combined with that 4. And then I'm going to subtract. Integrating x is simply x squared over 2, and then I'm going to subtract. Integrating x squared over 4 is going to be x cubed over 12, and that's from 0 to 4. Now the nice thing is when I go to plug in 0, I'm going to get 0 for that entire function, so I don't need to worry about subtracting it. All I care about now is when I plug in 4. So I'm going to have pi times plugging in 4. It's going to be easier to do the square root of 4 before cubing it. So the square root of 4 is 2. 2 cubed is 8. So 8 times 8 is going to be 64, and that's over 3. And then I'm going to subtract. 4 squared is 16. 16 divided by 2 is 8. And then 4 cubed is going to be 64. So that's 64 over 12. And again, like I said, when I plug in 0, that all goes away, so I'd be subtracting 0. So let's go ahead and simplify this down. I'm not going to mess with this whole number 8 right away, but I know that 64 and 12 are both divisible by 4, which will give me a fraction with a common denominator. So I'm going to do pi times 64 over 3 minus 8 minus dividing 64 by 4 gives me 16, and dividing 12 by 4 gives me 3. So that's going to allow me to combine 64/3 and 16/3. So I'll have pi times 64 minus 16 is going to be 48. So that's 48/3, which 48 divided by 3 is 16. So I'm going to have 16 minus that whole number 8. That's going to give me 8 pi as the volume once this region is revolved around the line y equals -2. Let's continue on to the next practice problem. We have that same exact region, so I'm just going to fill in what we already figured out. We're revolving this region, and we know the intersection points are 0, 0, and 4, 2. This time, however, we're revolving around the line y equals a +3. So we're going to be up here. So if we're thinking about revolving this and we want to use the disk washer method, because that's all we know at this point, which way are we going to draw those rectangles? Well, not horizontally, because that's going to give us a shell or a cylinder when we rotate it. We want to draw our rectangles vertically so that we get that nice disk or washer. So I'll go ahead and just fill in a couple rectangles so we get the idea. So our bounds are going to be the same as in that practice problem number 1. We're going to go from 0 in the x, drawing those rectangles, all the way up to 4 in the x. And we're also going to have pi, except our outer radius and our inner radius are going to change a bit. Because remember that radius is the distance from our function to the line we're revolving around. And our outer radius is that larger distance. So this time, our outer radius is going to go all the way to the blue function. So our outer radius function has completely switched. And also, let's think about how we're actually going to figure out that distance. And something to think about is we know this distance here to here. This distance is from the axis to our function. So that distance is x over 2. But I don't want that distance, I want the rest of that distance to get to our axis. And I know that full length, at least. I know that full length from our axis all the way to the line we're revolving around. Well, if that line occurs at y equals 3, that's a total of 3. So if I know that entire distance and I know the chunk I don't want from that distance, all I'm going to do is subtract. So that red line that I drew is my outer radius, and that outer radius is 3 minus x over 2. So I'm going to have 3 minus x over 2, and I'm going to square that because that's my radius squared. This red line is 3, that total distance, minus the chunk I don't want, which is that x over 2. The same concept is going to apply for our inner radius, except now we're going from that line to the function the square root of x. So I know that total distance is 3, and the distance I don't want included in that radius is this square root of x, height. So again, I'm going to be taking 3 and subtracting the square root of x from it, and then squaring that quantity. So here's my outer radius squared minus my inner radius squared, and that's all with respect to x. Let's go ahead and solve this out. So we'll go 0 to 4, and this will be pi times 3 minus x over 2, when I expand that out, is going to be 9 minus 6x over 2, which will be 3x, plus x squared over 4. And then I'm subtracting 9 minus 6 square root of x plus a positive x, because the square root of x squared is x, and this is all with respect to x. Just like above, let's simplify down. So we have 0 to 4. I'll go ahead and pull this pi out in front because it doesn't matter where I have it. My 9, you can see, will cancel out. My negative 3x can be combined by subtracting x from that. So I'll have a negative 4x. Then I can't combine anything else, so I'll add an x squared over 4. You can see I'm subtracting a negative 6 squared of x, which is the same as adding that positive 6 squared of x. Integrating all of this with respect to x. So negative 4x becomes negative 2x squared. X squared over 4 becomes x cubed over 12. And then 6 squared of x, remember that x goes to the power of 3/2. So then when I take 2/3, but I'm multiplying that by 6, that's really going to be 12 over 3, which simplifies down to 4. So I'm going to have 4x to the 3/2. And this is all evaluated from 0 to 4. So let's go ahead and start by plugging in 4. So I'll get negative 2 times 4 squared is going to be negative 2 times 16, which is negative 32. And I'll be adding that to 4 cubed over 12, which is 64 over 12, which we know from above, 64 over 12 simplified down to 16/3. So I'll go ahead and do that to make my life a little bit easier. So this will be 16/3, and then I'm going to be adding that to, if I take 4 and raise it to the 3/2, that's the same as 2 cubed, which is 8, and 8 times 4 is 32. And you see, this simplifies down nicely. Negative 32 cancels out with 32, so 16 pi over 3 is my volume in practice problem number 2. Let's move on to the next one. Still doing the same exact region with the same exact functions. I said that we were going to do the same functions on this entire worksheet just to make it a little bit easier on ourselves. So the intersection points are 0, 0 and 4, 2. However, for practice problem number 3, we're going to be revolving region R around the line x equals negative 2. So I'll go ahead and draw that line here, and this is what we're revolving around. Now, in order to use the disc washer method, which way am I going to draw my rectangles? If I drew them vertically, we would get that cylinder, which we don't want. I'm going to draw them horizontally, so I get that nice flat disc. And with drawing them horizontally, that means I'm going to be integrating with respect to y. So now, where I start drawing those rectangles and where I stop drawing those rectangles, I want the y bounds. So my y bound is 0, and my y bound is 2. So I'm going to go from 0 to 2, pi. Now I need my outer radius squared minus my inner radius squared. So my outer radius is going to be from the line I'm revolving around all the way to that farthest function, which is that blue function. Now this is very similar to up above, except if we're integrating with respect to y, what do we want our function in terms of? Not x. We don't want x variables in there. We want it in terms of y. So this blue line, which represents y equals x over 2, I'm going to rewrite that in terms of y. So this is going to be that x equals 2y. I know my distance from the y-axis to the blue line. That distance is 2y. But what is my distance, that total distance, which is the red line? Well, that's going to be 2y plus whatever this distance is here. And that chunk is going to be a distance of 2 because my line is x equals -2, and that's 2 units away from my y-axis. So I'm going to need to do a radius of 2 plus 2y. So I have 2 plus 2y, that quantity will get squared. That's my outer radius. Now I'm going to subtract my inner radius, which is going to be from the line I'm revolving around to that closer function, which that function was the square root of x. I don't want this in terms of x though. So the square root of x, if that's equal to y, when I solve for x, that's going to be that x equals y squared, and it is indeed that positive y squared because we're above that x-axis. So I'm going to say that I know this distance from my axis to my function is y squared, and I'm going to add that to my distance that I also know is 2. So 2 plus y squared is going to give me that inner radius. So 2 plus y squared gives me my inner radius, and I need to square that radius because that's my inner radius squared. And I'm going to integrate this with respect to y. Let's go ahead, quickly together, expand this out, simplify, integrate, and solve. I'll go ahead and pull that pi out in front. We're going from 0 to 2, expanding 2 plus 2y out. That's going to be 4 plus 8y plus 4y squared. And I'm going to be subtracting that inner radius squared, which is going to be the expansion of 2 plus y squared, which is 4 plus 4y squared plus y to the 4th. Now I'll simplify this down. You can see that my 4's will cancel out. There's nothing that can be combined with 8y, so this will remain as 8y. 4y squared minus a positive 4y squared goes to 0, so those cancel out, and then I'm just subtracting my y to the 4th and integrating that with respect to y. So that's going to be pi times integrating 8y becomes 4y squared, and integrating y to the 4th becomes y to the 5th over 5. And my y bounds are from 0 to 2. So plugging in 2, I'm going to get pi times 4 times 2 squared is going to be 4 times 4, which is 16, minus 2 to the 5th over 5 is going to be 32 over 5. And I'll subtract, plugging in 0, which is just subtracting 0. So now I need to find a common denominator in order to combine these terms. So what I need to do is put everything in terms of fifths. So this is going to be pi times 16 times 5 is 80. So that's 80 fifths minus 32 fifths. 80 minus 32 is 48. So the volume here is going to be 48 pi over 5. All right, completing one more example. Let's fill in what we know. Well, we're revolving this region, just like the previous three. Our intersection points are 0, 0, and 4, 2. This time, we're going to be finding the volume when it's revolved around x equals 4. So that's going to be this line here. So if I'm revolving around this line, first question, which way am I drawing my rectangles? to get that disk, it's going to be horizontally. So that means right off the bat, I know I'm integrating with respect to y. And I already know my y bounds starting at 0 and going to 2. So now I just have to find my outer radius, square it, and subtract my inner radius, squaring that, and multiply that all by pi, and integrate it with respect to y. So in this case, my outer radius goes from the line I'm revolving around to the furthest function that's away from that, which happens to be the red function. Now remember, if I'm integrating with respect to y, I want things in terms of y. So that function, the square root of x, in terms of y, was the function y squared. However, my radius, I need to know that distance. I know my distance from my y-axis to that point is going to be the function itself in terms of y, which is y squared. But that's the part that I don't want. I want to know that red line that I drew, that distance. And the other piece of information we know is we know that this full distance is going to be a positive 4, because that full distance of 4 is the distance from my y-axis to the line I'm revolving around. That's 4 units, and the chunk I don't want is that y squared. So my outer radius is going to be 4 minus y squared. That whole chunk, subtracting this chunk, will give me the chunk I want. So 4 minus y squared is that radius, and it's that outer radius, so I'll square that. Now my inner radius, the same concept. I know that total length is 4. My inner radius goes from that line x equals 4 to the blue line, which was x over 2, but in terms of y was 2y. So I know my distance to that point is 2y. I know that total distance from line to axis is 4, so I'm going to do 4 minus 2y to get the chunk that I want. So this is going to be 4 minus 2y, and that's the radius, so I'm going to square that and integrate this all with respect to y. So let's go ahead and expand all of this out. So 0 to 2, I'll go ahead and pull that pi out in front. 4 minus y squared squared is going to be 16 minus 8y squared, and then y squared times y squared, that's going to be a positive y to the 4th. And then I'm subtracting, expanding out 4 minus 2y squared, that's going to be 16 minus 16y plus 4y squared. And that's all integrated with respect to y once I simplify it down. So we'll have pi going from 0 to 2. You can see that my 16s will cancel out. And the only other thing that will help me simplify down is combining my negative 8y squared and subtracting 4y squared. So that'll be a negative 12y squared. And then I'll add my y to the 4th and subtract a negative. So I'll add that positive 16y. Now let's go ahead and integrate and then plug in our bounds to solve. So negative 12y squared, when I integrate that, y cubed over 3, that'll be negative 4y cubed. Then y fourth is going to be y to the 5th over 5, and then 16y, integrating that, is going to be 8y squared. My bounds in the y are from 0 to 2. So when I plug in 2, I'll get pi times 2 to the 3rd is 8, 4 times 8 is 32, so that'll be negative 32, plus y to the 5th is going to be 32 over 5, so 2 to the 5th over 5, plus 8 times 4 is going to be a positive 32. And I'm subtracting, plugging in 0, so I don't even need to worry about plugging that in. Negative 32 cancels out with 32, so my final solution is going to be 32 pi over 5 as my volume for practice problem number 4. Now, if you continue on to that page number 3, all I did was add the graph that we had used in each of these problems. And I added it quickly because I wanted to talk about changing the line we're revolving around. So when using the disk method, when we drew our line below, we had to take that distance and add it to either of the functions to get the outer radius and the inner radius. When we drew our line above, we had to take that distance and then subtract those functions to get the outer radius and the inner radius. When we drew it to the left, we needed to add that distance with the function. However, that function had to be in terms of y in order to get the radius. And when we drew it to the right, we had to take that distance and subtract those functions in terms of y in order to get the outer radius minus the inner radius. So you can see, depending on whether your line lies above, below, to the left, or to the right, you're either going to take that line and add the function, or you're going to take that value of the line and subtract the function. It just depends on where that line lies. And with that, we wrap up these examples on revolving around a line other than the X or Y axis using the disk and washer method. In the next video, we're going to finally jump into the shell method, and in that video, I'll combine rotating around axes and non-axes all in the same worksheet, because similar concepts apply. That radius is that distance, and that's what we're looking for to help us solve these problems. So continue on to the next example video to practice the shell method. But until then, good luck with your online learning.